In math, a dilation is a type of transformation that changes the size of a figure without changing its shape or orientation. Dilations are defined by two key components: a center of dilation, which is a fixed point that doesn't move when the figure is dilated, and a scale factor, which is a number that determines the amount of resizing or how you're scaling the figure up or down. Over here, there is a picture of a scale factor of 2. And as you can see, a scale factor of 2 makes the original figure bigger. And it does that by moving each of the points double the distance away from the center of dilation than it is at the beginning. Over here, we have a dilation of 1/2. And as you can see, the original figure is getting smaller. And the way that it's made smaller is each of the points on the figure is moved closer to the center of dilation. The distance is decreased by half to bring it halfway closer to the center of dilation than it originally was. And in these two pictures, we have a negative scale factor. And what a negative scale factor does is reflects the figure or flips it over. Here is an example of a negative scale factor that is greater than -1. So it does make the figure bigger, but it flips it over. And over here, we have a negative scale factor that is a fraction, 1/2, in between 0 and 1. So it makes the figure smaller. But as you can see, it also reflects it over. So a negative scale factor changes the size, makes it bigger or smaller, depending on the scale factor, but it also flips it over or reflects it. When a dilation occurs, corresponding angles stay congruent and corresponding sides are proportional. And the corresponding sides are proportional by the scale factor. The scale factor is often called K. So if you see K, K means the scale factor. And as we were talking about on the last slide, if your scale factor is bigger than 1, like if it's 1, 2, 3, 4, 5, 10, 100, a million, your figure is going to get bigger. The sides are all going to get multiplied by that scale factor, and they're going to get that many times bigger. And if your scale factor is in between 0 and 1, if it's a fraction, 1/2, a third, a fourth, anything in between 0 and 1, your original figure is going to get smaller. Each of the sides are going to get multiplied by that scale factor that makes it smaller. As you can see over here in this picture, the original triangle is triangle PBC. As you can see by the letters, it doesn't have the primes on it. When it has the primes, that means the image. So triangle PBC, the larger triangle, is the pre-image. And the smaller triangle over here is the image. And if I wanted to find the scale factor, if the numbers are easy, like they are on this side and this side over here, then we can tell by just looking. We can say, okay, in order to get from the bigger triangle to the small triangle, to get from 3 to 1, it's a third. Because if we were going from 1 to 3, it would be multiplying by 3. So going the other way, it's multiplying by a third. You're getting a third smaller. But if the numbers were a little bit tricky to see just from looking at them, like on these two corresponding sides over here, the 2/3 and the 2, one way that you can find what the scale factor is always is you can take a side from the image and you can divide by a corresponding side from the pre-image. So here, a side from the image would be 2/3. And its corresponding side from the pre-image would be 2. And if you do that on your calculator and you divide 2/3 divided by 2, you should arrive at the scale factor, which here is 1/3. So by taking a side from the image and dividing by the corresponding side from the pre-image, you can always find what your scale factor is, even if the numbers aren't very nice. Here we have some examples based on what we just spoke about. For the first one, it's telling us that triangle GHJ is dilated by a scale factor of 1/2. So we know that that's going to make the figure smaller, half smaller. And the dilation is centered at point B. And triangle GHJ is going to get mapped onto triangle CDF. So triangle CDF is after the dilation, it's the image. It's saying if the measure of angle DFC is 40 degrees, what is the measurement of angle HJG. So what's the measurement of this angle over here? Pause the video, think about it, pick an answer choice, and then unpause. The correct answer is answer choice number 2. This angle over here is also 40 degrees. And that's because when you have a dilation, the corresponding angles before and after the dilation are congruent to each other. If we take a look at the next question, it's saying that triangle TAP is dilated by a scale factor of 1/2. So it's getting smaller. And it's saying which statement about the image, triangle T prime, A prime, B prime, is true. If we wanted to, we could draw a picture to see what's going on. So I can say that this is the original triangle, triangle TAP. And I'll just label it in the same order. This could be triangle T prime, A prime, P prime. So the image is half the size of the original, so it's just an estimated picture. And it's saying which statement about the dilated triangle has to be true. So the first one says the measure of angle T prime, A prime, P prime, so this angle over here, is half the measurement of its corresponding angle in the original angle TAP. And that sounds reasonable because the scale factor is 1/2, so this should be half of this if it were talking about sides. But since it's talking about angles, we know that after a dilation, corresponding angles are congruent. So the corresponding angles actually don't change the measurement. So the angle over here and its corresponding angle over here would actually have the same measurement. So that one is not the right answer choice. Using that same reasoning, answer choice 2 is also wrong because it's talking about corresponding angles again, and it's mentioning that they change measurements, that this is getting doubled. So that one's gone because corresponding angles stay congruent before and after a dilation. Answer choices 3 and 4 are talking about the side measurements, so one of these should be the correct answer. Answer choice 3 is saying TA is double T prime, A prime. That makes sense because the dilation is 1/2, so this should be double the dilated corresponding side. The fourth answer choice says that this is half of this. That doesn't make sense because the dilation is 1/2, so this one's smaller, so this one can't be half of this one. This one has to be half of this one. So answer choice 3 is the correct answer choice. For this one over here, it's saying that triangle RST is the image of triangle ABC after a dilation centered at point P. So triangle RST is the image, so this is the pre-image. So the dilation made the triangle smaller. The scale factor of the dilation that maps triangle ABC onto triangle RST is what? You should pause the video, think about it, and then unpause. So I'm going to pick a pair of corresponding sides, and then I'm going to do what we talked about on the slide over here to find the scale factor. And I'm going to take a side from the image, and I'm going to divide by a corresponding side from the pre-image in order to find the scale factor. Now, I'm not going to pick the slanted sides because that's going to be hard for me to find the exact measurement of. I'm going to pick a pair of corresponding sides that's easy for me to find the measurement of. So I'm going to take the vertical sides over here, this one RS, and the one that corresponds to it over here, AB. And since the dilation happened, it's the same scale factor for all 3 pairs of corresponding sides, so it doesn't matter which pair of sides I choose, it's the same scale factor because the dilation decreases or increases proportionally. So this is 1 box, so that's 1. And this is 1, 2, 3 boxes. And then to find the scale factor, it's side from image, so this smaller triangle is the image, divided by corresponding side from pre-image. So the scale factor is 1/3, and it makes sense because the dilation is getting smaller, so it makes sense that it would be a fraction. For the next one, it's saying that triangle A prime, B prime, C prime is the image of this triangle after a dilation centered at the origin, and it's giving us the coordinates of A, B, and C. Down here, it's telling us the coordinates of A prime are -4, 2. If the coordinates of A prime are -4, 2, then what are the coordinates of B prime? So in order to figure out how to get B prime, I need to figure out what the scale factor was of this dilation. So in order to do that, I'm going to compare point A and point A prime. So point A is -2, 1. And point A prime is -4, 2. So to get from this x coordinate to this x coordinate, -2 times 2 gives us -4. And to get from this y coordinate to this y coordinate, 1 times 2 gives us 2. So since the x and y coordinate are both being multiplied by 2, the scale factor over here is 2. And that's actually a rule for when you have a dilation centered at the origin. In order to find the dilated points, you can take the original point and you could multiply the x and y coordinate by the scale factor in order to find the dilated point. So in order to find B prime, all we have to do is take the x and y coordinate of B and multiply by the scale factor, which we now figured out was 2. So the x coordinate was 2, so 2 times 2 is 4. The y coordinate is 4, so 4 times 2 is 8. So the coordinates of point B prime are 4, 8, which is answer choice number 2. For this next one over here, it's telling us that triangle ABE is the image of triangle ACD after a dilation centered at the origin. So this one is a dilation getting smaller because the smaller triangle is the image and the bigger triangle is the pre-image. It gives us the coordinates of the points. And it's asking us for what the ratio of the lengths of BE to CD are. So BE and CD are these slanted sides over here. So remember, in a dilation, the scale factor is the same for all 3 pairs of corresponding sides. So whatever the ratio is for the other sides, it's going to be the same as for those slanted sides. So I'm going to pick sides that are easier for me to find the scale factor of. So instead of picking the slanted ones, I'm going to pick ones that are vertical or horizontal. But point C over here is kind of in between a box. So that's going to be a little difficult for me. So I'm going to pick AE from the small triangle and its corresponding side AD from the big triangle. They land on clear points and they're vertical lines, so I can easily count the boxes. So for AE, that's 1, 2, 3, 4 boxes long. And for AD, 1, 2, 3, 4, 5, 6 boxes long. And to find the scale factor, it's side from image divided by corresponding side from pre-image. So the smaller triangle was the image, so that's 4. And its corresponding side had a length of 6. If we reduce 4 over 6, if we divide the top and bottom by 2, we get 2/3. So the ratio of BE to CD would be the same as the ratio from AE to AD, which would be 2/3. For the next one, it's telling us that triangle ABC is dilated by a scale factor of 2 to map onto its image, triangle RST. So we have the pre-image, the smaller triangle, and the image, the larger triangle. And it's asking for what the coordinates of the center of dilation are. So remember that when you're doing a dilation, the center of dilation, the pre-image point, and its corresponding image point should all lie along the same line. They're all collinear. So what I'm going to do is I'm just going to connect a line between all of the pre-image points and the corresponding image points. And then I'm going to see where they meet. And that should be where the center of dilation is, because all should have the same center of dilation. So R is the image point, and A is its corresponding pre-image point. So I'm going to just use my straight edge and just connect a line from R and A through A going outwards, so we can find what the center of dilation is. Then I'm going to connect S and B because those are corresponding pre-image and image points, and I'm just going to extend it, because the center of dilation should be on the same line as the image point and its corresponding pre-image point. And I'm going to do the same thing over here. I'm going to connect image and corresponding pre-image point and just extend it a little bit, because once again, the center of dilation should be on the same line as the pre-image point and the corresponding image point. And then we can see where they intersect. And they intersect right over here at this point, which is the point 2, 1. So 2, 1 is the center of dilation here. Now we're going to talk about constructing dilations. So what we're going to do is we're going to dilate this triangle centered at point C by a scale factor of 2. So we're going to make this triangle end up being double the size that it is right now. And since C is the center of dilation, C is not going to move. C is going to stay here. So all we really have to do is dilate points A and point B. So in order to do this dilation, what we're going to do is we're going to take point A, we're going to measure how far it is from the center, and we're going to double that distance. We're going to move it double further away from the center than it is right now, and the same thing with B. And by moving each of the points further from the center, we're going to actually make it bigger. As we spoke about before, the center of dilation, the pre-image point, and the corresponding image point should all be located along the same line. They're all collinear. So I just started off first with my straight edge, connecting between the center, the pre-image point, and just extending the line, because the image point is going to be located somewhere along this line. I'm going to do the same thing over here for point B. I'm going to just extend my line, because the center, the pre-image point, and the corresponding image point should be along the same line. So B prime is going to be somewhere along this line. Now let's actually find where A prime and B prime are. So I'm going to put my compass let me just spin this around because I want to put my compass point on point C. So I'm going to put my compass point on point C. There we go. Now I can move my compass. And what I want to do is I want to measure as best as I can to point A. And then I'm going to put a little arc to show I measured. So what we're doing is measuring how far point A is from the center of dilation. And once we have the measurement of how far A is from the center of dilation, we can just double that distance. And if you needed a scale factor of 3, you could go over here and you could triple it. You could do it again if you needed a scale factor of 4, but this is just a scale factor of 2. So over here is A prime, and it lies along the same line as the pre-image point and the center of dilation. And we made this point by doubling the distance that A was from the center of dilation. Now we are going to find B prime. So we're going to do the same process. We're going to put our compass on the center, and we're going to open up until we match up with B. Then I'm just going to put an arc to show that I measured. And that's the distance from the center of dilation to point B. And now we're just going to use that measurement again. Oops, I moved the compass. Now we're going to use that measurement again to find point B prime. And if you needed a scale factor of 3, you could just use that measurement again and use the same thing. So on if you needed a scale factor of 4, but this is just asking for a scale factor of 2. And now, if I connect our image points together, A prime, B prime, and C prime, which is the original point C because it was the center of dilation, so it didn't change. Notice how the new dilated triangle is double the size of the original. We increased it by double the size by taking each of the points and moving it double the distance from the center than it already was. We're going to do one more construction in this video. We're going to do another dilation by a scale factor of 1/2 this time. And this one again is going to be centered at point C. But this time instead of a scale factor of 2, we're going to be doing a scale factor of 1/2. So this triangle is going to get half smaller. So instead of moving point A further from point C, like we did for the scale factor of 2, we're actually going to move it closer to point C. We're going to move it halfway closer. So what we need to do is we need to find what half the distance is from A to C. And we're going to do that by making a perpendicular bisector, because that's going to cut it in half, find the midpoint, so we can see what half the distance is. So it doesn't matter how far you open your compass. You can match it exactly to point C. You just need to open it more than halfway down the line segment, and then just an arc above and below. And then we're going to go over to point C. And you could make full circles if you want, but I'm just making arcs. And through that intersection, you can draw your perpendicular bisector. And where it hits the side of the triangle, that's point A prime, because it is halfway in between A and C. So it's half the distance that the original point A was from point C. And now we just need to do the same thing for point B. So I'm going to put my compass point on point B, and I want to find half the distance that B is from C. I'm going to use a different color for this. So it doesn't matter, once again, how far you open the compass. You could match it exactly up to point C if you wanted to, but it just has to be more than halfway down the line segment. So I'm just going to make an arc above and below. And once again, you could make a circle if you want to, but all the circles get confusing. And then I'm just going to intersect it. And through the intersection, we can make our perpendicular bisector. And where it hits the side of the triangle is point B prime. Point C doesn't change because that is our center of dilation. And now if I connect all the points together, so A prime, let me use a better color than that. Use black. If I connect A prime, B prime, and C together, notice that the resulting triangle is half the size of the original. And we made it half the size by taking each of the points and having the distance from the center of dilation that it already was. The last thing we're going to talk about in this video is line dilations. So dilating line equations. So dilations preserve parallelism, and parallel lines have equal slopes. So if we take a look at the example that I have underneath, where it gives us the equation of a line T, and it tells us that line M is the image of line T after a dilation with a scale factor of 1/2 centered at the origin. What we need to do is we need to write the equation of this line. So the dilated line, we need to write the equation of. The first thing we have to do is take the original line, and we need to get it into y equals mx plus b format, which is our standard way of writing the equations of lines, so that we can easily see what the slope and the y-intercept is. So I want to get the y by itself. So I'm going to subtract the 3x from both sides. And that cancels out over here. I'm going to bring down the negative y. Don't forget the negative. And then we can write this as 6 minus 3x. But I'm just going to write it as negative 3x, so the 3x part first, plus 6. Just so it could be in y equals mx plus b form. But if you wrote 6 minus 3x, it's the same thing. And then there's an invisible 1 here if you don't see a coefficient. So we just need to divide everything by negative 1 to get y by itself. So we have y equals 3x minus 6. So this is the equation of the original line in y equals mx plus b form. So since dilations preserve parallelism and parallel lines have equal slopes, the dilated line should have the same slope as this line. So the slope of this line is 3. So the dilated line should also have the same slope of 3. And we usually use m for the slope because in y equals mx plus b, in the equation of a line, m is the slope and b is the y-intercept. So now we just need to find what the dilated y-intercept is going to be. So we do have a rule that when we're dilating a line equation and we are centered at the origin, we can take the y-intercept and we could multiply it by the scale factor. The scale factor here is 1/2. So if I take negative 6 and I multiply it by the scale factor, because negative 6 is the y-intercept of the original equation, I get negative 3. So the new y-intercept of the dilated line should be negative 3. So the equation of our dilated line should be y equals 3x, because the slope is 3, minus 3, because the y-intercept is negative 3. So anytime you have a line equation centered at the origin, the slope stays the same after the dilation, because dilations always make parallel lines, so the slopes will always be the same. You could take the y-intercept and multiply it by the scale factor. This one over here is a little bit different. Aaliyah says that when the line 4x plus 3y equals 24 is dilated by a scale factor of 2, centered at the point 3, 4, the equation of the dilated line is y equals negative 4 over 3x plus 16. Is Aaliyah correct? So we can start off with the same process that we used before. We can take the original line and we can put it into y equals mx plus b form, so we can clearly see what the slope and the y-intercept is. So let's move everything away from the y. So we're going to subtract 4x from both sides. And we have 3y is equal to, you can write it as 24 minus 4x, but I'm just going to write the negative 4x first, plus 24. So it's in y equals mx plus b form. Then we can just divide everything by 3 to get the y by itself. So we have y equals to negative 4 over 3x. That doesn't divide nicely, so you can just leave it as a fraction. 24 divided by 3 is 8, plus 8. So this is the equation of the original line in y equals mx plus b format. And now we can see that the slope of the line, of the original line, is negative 4 over 3. So it makes sense that the dilated line would have the same slope, because dilations make parallel lines which have the same slopes. And based on what we talked about in the last example, since the scale factor is 2, and 8 times 2 is 16, it would make sense that you could take the y-intercept and multiply it by the scale factor to get the new y-intercept. But the last question that we did, the center of dilation was at the origin. The center of dilation here is at a different point. It's at the point 3, 4. So if I graph this equation really quickly, so the y-intercept is 8. 1, 2, 3, 4, 5, 6, 7, 8. We always start graphing with the y-intercept. So I just dotted it on the y-axis. And then the slope tells us to go down 4 and right 3 to get more points. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. That's all the points that will fit on my grid. And I'll put arrows on the end. And now let's look for the center, the point 3, 4. 1, 2, 3, 1, 2, 3, 4. It's right over here. So the center of dilation is actually on the line, and that changes things, because if you're dilating with a center that's on the line, all of the points are just going to shift along the same line. So it's actually going to result in the same line as the original line. So Aaliyah isn't correct. Aaliyah would be correct if the dilation was centered at the origin, because then she would be using the right rule that you take the y-intercept and you multiply it by the scale factor. But since the center of dilation is on the line and points are just going to shift along the same line, it's going to result in the same line as the original. So the dilated equation would be the same as the original, y equals negative 4 over 3x plus 8. To summarize, when a line dilation is centered at the origin, you multiply the y-intercept by the scale factor. When a line dilation is centered at a point on the original line, it results in the same line as the original line, as points will shift along the same line. The slope always remains the same as the original line after a dilation.